375 million years ago, the first forests appeared on Earth. Within 20 million years, 75% of all ocean life was dead. These were not the forests we know today. They were dominated by a single organism called Archaeopteryx. Trees 30 meters tall with trunks 1 meter thick and roots plunging deep into bedrock. They spread across every available landmass, covering Euramerica and Gondwana in dense, continuous forest. The armored fish that had ruled the seas for 70 million years were gone completely. The massive reef systems built by ancient corals and sponges collapsed, leaving a gap in the fossil record that would last over 100 million years. The trilobites that had survived for 270 million years were reduced to a single surviving order. The mechanism was indirect, almost elegant in its cruelty. These trees did not attack the ocean. They attacked the atmosphere. Their roots broke down bedrock, releasing nutrients that washed into the seas. The forests stripped carbon dioxide from the air, triggering glaciation. The nutrient pulse fed algal blooms that consumed all the oxygen. Life's conquest of land nearly ended life in the water. To understand how forests killed the ocean, you need to see what the world looked like before trees existed. Early Devonian continents were bare rock. No soil, just stone. Plants hugged the coastlines like green slime. They were small organisms, maybe 30 centimeters tall, with shallow roots that barely scratched the surface. They were pioneers, but they could not venture far from water. Then, around 385 million years ago, something changed. Archaeopteryx appeared. This was not just another plant. It was the first organism that looked like what we would call a tree, and it possessed 3 innovations that would reshape the planet. The first was lignin, the complex polymer that makes wood. Before lignin, plants were soft, floppy things. Lignin provided structural rigidity, allowing Archaeopteryx to grow 30 meters tall and compete for sunlight. More importantly, lignin was nearly impossible to decompose. When these trees died, they did not rot. They accumulated in swamps, forming the first major coal seams, locking carbon out of the atmosphere permanently. The second innovation was leaves. Not the spine-like structures of earlier plants, but true laminar leaves with massive surface area for photosynthesis. More surface area meant more carbon dioxide pulled from the air, more water transpired, and more aggressive interaction with the atmosphere. The third innovation was the killer, deep roots. Early plants had thread-like roots that penetrated maybe a few centimeters. Archaeopteryx roots burrowed meters into bedrock. They did not just anchor the tree, they mined the rock itself. These roots secreted organic acids that dissolved minerals such as calcium and magnesium from the surrounding stone. This was chemical warfare conducted by millions of trees across millions of square kilometers. Silicate weathering is Earth's natural thermostat. Rain falls and combines with carbon dioxide to form a weak carbonic acid. That acid dissolves rock minerals, and the dissolved ions wash into the ocean, where they precipitate as limestone, permanently locking carbon dioxide into rock. Before Archaeopteryx, this process happened slowly. Plant roots accelerated it by orders of magnitude. Quantitative estimates suggest weathering rates increased to between 1.64 and 10 times baseline levels. Root systems increased the surface area of rock exposed to chemical attack. The organic acids they secreted were far more corrosive than rainwater alone. The soil they created, the first deep structured soil in Earth's history, retained moisture and kept the weathering reaction running continuously.
For the first time since life began, the continents had soil, meters thick, held together by root networks.
This soil promoted weathering through multiple mechanisms. It provided reactive surfaces for water-rock interaction. Respiration by roots and soil microbes elevated soil carbon dioxide concentrations to levels 10 to 100 times atmospheric levels, creating concentrated carbonic acid that aggressively dissolved silicate minerals. The two mechanisms, direct photosynthetic drawdown and root-enhanced weathering, operated simultaneously. One pulled carbon directly from the air in decades. The other operated over millennia, and it was relentless. Atmospheric carbon dioxide began to fall. Estimates suggest it dropped from 4,000 parts per million to somewhere between 300 and 400 parts per million.
A decline of roughly 90%. The greenhouse blanket that had insulated Earth for tens of millions of years was disintegrating.
And the forests did not stop spreading. By the middle of the late Devonian, vast swaths of Euramerica, the region that would become Eastern North America and Western Europe, were covered in dense, continuous forest. Gondwana's northern margins supported their own stands. Every new root system drew down more carbon dioxide. The consequences were measurable. Oxygen isotope ratios preserved in the teeth of conodonts, tiny eel-like vertebrates, provide a direct record of seawater temperature. The data show a clear cooling trend. Tropical sea surface temperatures fell by 5 to 7 degrees Celsius during the crisis. This was not a gentle decline. It was a plunge. Carbon dioxide is a greenhouse gas. Remove 90% of it, and you remove 90% of that heat retention. Global temperatures began to drop. The tropics cooled. Mid-latitudes became seasonally cold. And at the poles, conditions became suitable for ice. Here's where geography mattered. During the late Devonian, the supercontinent Gondwana was drifting across the South Pole. When atmospheric carbon dioxide was high, back at 4,000 parts per million, this positioning did not matter. The greenhouse effect kept even polar regions relatively warm, but with carbon dioxide levels now crashing toward 300 parts per million, the South Pole became cold enough for snow to accumulate and not melt. The snow compacted into glaciers. The glaciers spread, thickening into ice sheets. Ice has a feedback effect. It reflects sunlight back into space, 60 to 90% compared to the ocean's 6%. The more ice there is, the colder it gets, and the more ice forms. This is called the albedo feedback, and it is ruthless. The geological evidence is tillites. Tillites, lithified glacial deposits consisting of unsorted rock debris, appear in the Parnaíba, Jatoba, and Solimões basins of Brazil. Striated bedrock surfaces in Niger and Bolivia exhibit the characteristic pattern of scratches left by glacial ice advancing across rock. Dropstones, clasts dropped from melting icebergs into fine-grained marine sediments, have been found as far north as the Appalachian Basin. The distribution of these deposits confirms that ice sheets covered millions of square kilometers of South America and North Central Africa. This was not alpine glaciation confined to mountain peaks. This was continental-scale ice. The ice locked up the water. Oceans are a closed system. If a significant portion of water gets trapped as ice on land, sea levels must fall. During the late Devonian glaciation, global sea levels dropped by an estimated 80 to 120 meters, over 300 feet. For a planet whose continents were covered in shallow inland seas, this was catastrophic. The Devonian world was characterized by vast epicontinental seas like the Kaskaskia Sea that covered much of the North American craton. These shallow, sunlit waters were the primary habitat for the era's diverse marine life. The sea level drop drained these basins, exposing thousands of square kilometers of continental shelf to the air. The reefs, the brachiopod beds, the placoderm hunting grounds were all exposed or pushed into restricted, deeper basins. And those deeper basins were about to become death traps. The creation of soil had a second consequence. For the first time in Earth's history, the continents had a layer of organic, rich material that could be eroded.
Before Archaeopteryx, rainfall just washed bare rock.
Now it washed soil rich in phosphorus and nitrogen liberated from bedrock by those aggressive root systems. These nutrients flowed into rivers and eventually into the oceans at concentrations never before seen. Phosphorus and nitrogen are limiting nutrients for marine photosynthetic organisms. In most oceans, they are scarce enough that algae and cyanobacteria populations remain relatively stable. introduce a sudden influx, and those populations explode. The late Devonian oceans received exactly that influx. Rivers draining the new Archaeopteryx forests dumped nutrients into warm, shallow inland seas. The result was algal blooms of unimaginable scale. Surface waters turned green and thick with microscopic life. These were not localized events, they were ocean-wide. When the algae died, either from nutrient depletion or overcrowding, their bodies sank to the seafloor. There, bacteria gathered to decompose them. Bacterial decomposition consumes oxygen. The more organic matter there is to decompose, the more oxygen gets used up. In the late Devonian, the amount of organic matter raining down on the seafloor overwhelmed the oxygen supply. The bottom waters went anoxic, depleted of dissolved oxygen. Fish, invertebrates, and anything that needed to breathe suffocated. The anoxia spread. Shallow seas that had been rich in life became dead zones.
The water likely turned toxic, reeking of hydrogen sulfide, the same chemical that gives rotten eggs their smell. As bacteria switched to sulfur-based metabolism in the absence of oxygen, creatures that couldn't swim away from the bottom died in place. The geological evidence for this event is unambiguous.
Around 372 million years ago, at a moment called the Kellwasser event, black shale layers appeared in sedimentary sequences around the world. These shales are black because they are packed with organic carbon, the remains of algae and other organisms that died and sank into oxygen-free water. Without oxygen, the carbon could not decompose. It accumulated layer upon layer, preserved in the rock record as a chemical signature of suffocation. The Kellwasser black shales appear in North America, Europe, North Africa, Australia, and Asia. Their global distribution confirms this was not a local catastrophe. The oceans had stratified. A thin surface layer churned by waves and exposed to air retained some oxygen. Everything below became a graveyard. The event was not a single blow. There were two closely spaced extinction pulses separated by roughly 800,000 years, with the second pulse more severe than the first. Two distinct anoxic shale layers mark these pulses in many sections globally. Reefs collapsed. The stromatoporoids, the rugose corals, the tabulate corals, the organisms that built these reefs were rooted in place. They could not move. When the water around them lost its oxygen, they died where they grew. The Kellwasser event wiped out reef ecosystems almost entirely. The planet limped on for another 13 million years. Carbon dioxide levels continued to fall as forests expanded and weathering intensified. The oceans remained unstable, lurching between periods of partial recovery and renewed anoxia. Marine biodiversity, already devastated, struggled to rebound. Then the temperature dropped far enough to trigger the second catastrophe. The Hangenberg event occurred approximately 13 million years after the Kellwasser event, and it took place around 359 million years ago at the boundary between the Devonian and Carboniferous periods. This time, the crisis combined severe anoxia with a massive glaciation-driven sea level drop. The Hangenberg Black Shale marks the beginning of the main marine extinction pulse. It records organic material deposited in anoxic, deep-water environments during a large marine transgression. Uranium-lead dating constrains the main pulse to between 50,000 and 190,000 years. The combination was lethal. Anoxia eliminated organisms in deep water. The sea level drop eliminated shallow water habitats. Marine life had nowhere to hide. The extinction was selective. It didn't kill randomly. It targeted specific vulnerabilities. Placoderms went extinct. Every species, every lineage, every evolutionary experiment within that group disappeared. Dunkleosteus and its armored relatives, which had dominated marine ecosystems for tens of millions of years, left no descendants. Their heavy armor, once an evolutionary advantage, became a liability. Armored fish are less efficient swimmers. They require more oxygen to maintain metabolic functions. In low oxygen environments, they struggled. Many were bottom dwellers, making them vulnerable to anoxic conditions that developed first at depth. Titanichthys, a suspension feeder, may have been killed by algal blooms clogging its gills. The great reefs were gone. Stromatoporoids, rugose corals, and tabulate corals collapsed. Reef ecosystems of comparable complexity would not appear again for over 100 million years, not until new types of corals evolved in the Triassic period. Trilobites were decimated. 3 major orders went extinct: Coryneoxochida, Harpatida, and Odontopleurida. Only the Proetida survived, smaller generalist organisms that tolerated deeper disaerobic environments. Trilobite diversity never recovered to pre-Devonian levels. Brachiopods and ammonoids suffered massive losses, though some lineages persisted. The victims shared characteristics. They were overwhelmingly marine. They were tropical or subtropical, adapted to warm, stable temperatures. They were shallow water organisms living in the inland seas that drained during glaciation. Many were bottom dwellers, vulnerable to anoxic conditions. The survivors were different. Sharks and ray-finned fish came through comparatively intact. These groups were more mobile, more adaptable, better suited to navigate unstable conditions. With the placoderms gone, an enormous ecological vacuum opened. In the Carboniferous, sharks and ray-finned fish exploded in diversity, filling niches left empty by extinction. The modern structure of ocean ecosystems, dominated by cartilaginous and bony fish, was established by this reset. Land plants were almost entirely unaffected. Archaeopteryx and its relatives continued to spread. The organisms that caused the extinction thrived. Then there were the tetrapods. Creatures like Acanthostega and Ichthyostega lived right at the boundary. They were 4-limbed vertebrates descended from lobe-finned fish, with adaptations for both water and land. They had lungs that allowed them to breathe air. They had limbs capable of supporting their weight on solid ground. At least briefly, they lived in coastal swamps and river deltas, exactly the environments most affected by anoxia and sea level changes. The water was becoming unlivable. Dissolved oxygen was plummeting. Shallow aquatic habitats were disappearing. The ability to leave the water, to haul out onto mud or rock and breathe air, wasn't an adaptation for exploration. It was an escape route. The tetrapod lineage may have survived not by moving towards something, but by fleeing something. Sharks and ray-finned fish radiated into vacant niches, becoming the dominant fish groups that persist today. Tetrapods survived by leaving the water. Our ancestors walked on land because the oceans were dying. The forests kept spreading. Carboniferous coal swamps pushed atmospheric oxygen to 35%.
The highest in Earth's history.
The lesson is specific. Life on land can destabilize life in the ocean through biogeochemical cycles. The coupling between terrestrial and marine systems, established in the Devonian, remains as potent today as it was 370 million years ago. If this story of how forests nearly killed the ocean left you questioning what other planetary catastrophes are hidden in the fossil record, hit that like button and subscribe. There are more uncomfortable truths buried in Earth's past.